Okay, so starting again. When we talk about energy, and we haven't talked about this yet, I can look right at you or you guys. The things to remember are the system and the surroundings are what we're talking about all the time, but sometimes it gets lost. So energy is something the system can have. The surroundings can also have energy, but we're almost always interested in the system's energy. Now, energy can move between the system and the surroundings. Energy is a state function. Those other functions, heat and work, are ways the energy gets from the system to the surroundings. So here's the system, and you can make the system anything you want. You can make it a beaker with a reaction going in it. You can make it just right down to the molecules. So the surroundings is the solvent, or the beaker is the surroundings. You can make the system whatever you want. Just put a barrier in your mind. Everything else is the surroundings. The system and the surroundings together is the units. So system and then everything else is the surroundings. Heat and work, you don't have those things. They all have units of energy, but heat and work are the ways you move energy between the system and the surroundings. So, for instance, if we put heat into the system, that's heat flow. Heat can go in or out. If it goes in, we usually give it a plus sign. And we give it a plus sign because heat going in tends to raise the energy of the system. So it should make delta E bigger, or it should make delta it should make delta E positive. So if the energy is going in, that should make delta E positive, so we just make Q positive if it's going in. So energy is Q plus W, so heat going in tends to make this positive. And of course then, heat going out, we would give a negative sign too. Okay? Hey, while you're listening, go down to the bottom and mute your mic. When you ask a question, remember to unmute it, but we can hear everything that's happening in Yali's. You got it? She's muted. Yeah. We don't hear you anymore, so you must have muted. Okay. Remember when you wanted us to hear you, though, unmute. So and work is exactly the same way. If work can transfer energy in or out. And usually with work, we say if work's done on the system, that's what makes the energy go up. If the system does work, energy goes down. And that should make you sense. It should take some of your energy to do work. So if you do work, your energy should go down. So this one's minus. This is doing work. This is work done on the system. Okay? So those things are super important to keep in mind because that helps you understand all the plots of energy that can always be confusing. So let's. How does the thin marker look? Good. Okay. Okay.
No, yeah, I can see it just as well. It looks good.
Okay, I mean, because thin seems a little easier, so I'll just go a little thinner there too. So let's just give let's first give some names. So if I look at Q positive, that's heat going into the system. We actually give that a name. Right? You guys know that endothermic. You heard that one? Oh, yeah. Endo. In fact, endo means in, and if heat comes out of the system, that's exothermic. So endothermic and exothermic are the kinds of reactions you can have. These are the fun ones, because that's when energy comes out and you get to see lights and explosions. These are dull and boring. This is energy or heat going into the system. So this helps with something that can sometimes be confusing. And let's do the example here of a set of charged objects. So let's say we have 2 tennis balls. They're charged, and charged objects, one's plus, one's minus, so they attract each other. Okay? So let's start with them at this configuration. Now, if they move apart, and I'm plotting energy going up and down here, if they move apart, do they go up energy or down? So is moving apart endothermic or exothermic?
It takes energy to move them apart, right? Because they want to stay together.
Mm-hmm.
So that would be endothermic because energy is going into the system.
Oh my God. I love that explanation. Did you hear that? Can you hear your roommate? Right, that's exactly the way to think about it. If you want to they attract each other. If you want them to be separated, you have to pull them apart. So they're the system, the two balls. I'm the surroundings, and I have to put that energy in to pull them apart. So, in fact, that's probably work. So if I do this, that system farther apart is higher energy, and the energy came from me.
Is that because they want to pull back together?
Yes. Yeah. So these two, if I drew them farther apart, I'd have to draw them higher up on the energy scale. So going from here to here, final minus initial is positive. This is a bigger number than this. So delta E for that is greater than 0. Delta E is positive for that. So that is endothermic. Everybody down with that? Now, the other way to go is to push them together. So they're already touching. So if they're 2 tennis balls, what do I have to do to get them closer than touching? I have to squish them. Yeah, I mean, I can try to get, they're not going to really get any closer, but I can try. And what do you have to do that? Yeah, that takes work too.
More work.
And probably more.
Because
So to squeeze on them, that's hard. And to get them to move at all will take a lot.
Yeah.
So if I want to squeeze them even a little, so they got squished here, even a little, it's hard to do. Okay?
and so that's also endothermic?
Yes, that also requires energy to do that. So now we've plotted these straight up and down in energy, and that's where they are. It would be interesting to spread them out in energy. So if we spread them out in this dimension, we didn't have any dimensions down there, and we made this dimension r, where r is the distance between them. So this one, we'll say that's that distance. These guys here are farther apart, so they're out there. These guys here are closer together, so they're here. Well, now we're gonna do something sucking cool. Oh my God, I'm so excited.
Are you gonna do the?
I'm gonna move them.
You're gonna make it small. Just
No,
wait,
I'm gonna move them.
just
I'm gonna
wait.
move them.
Oh.
So I'm gonna do this and say these
No fucking way. No.
go out there.
Oh, sorry.
And these
Wow.
here to here because they're the low radius. This is the middle, and this is the big.
Wait, and then it's one of these.
Oh my God! Then it's one of those. Exactly.
Oh.
where do the heck those things come from? So now if I plot, now I should be able to go continuously from here to here.
All
Oh, look at that.
Oh my God!
right.
This is really
It's one of those.
This is, wait, where have we seen this curve before? It's the ER thing, the one that like dips and then they go.
Because
it's
it's
the
energy
bond-
and radius.
bond thing, like charges coming together and sodium chloride pulling apart. Two charged particles coming together, a plus and a minus ion. Okay, or a bond. If you're breaking a bond, if this is just a bond, you have to do this too. To pull apart a bond requires energy. So the free atoms, the atoms far apart, are at higher energy than the atoms bound together
Because you had to put energy into the system.
to pull them apart. Okay,
Everything
so
makes
breaking
sense.
bonds is always endothermic. If you take nothing else home from Chem 1, take home the fact, break a bond that takes energy. And it should, because otherwise they wouldn't stay together on their own, right? They would just spontaneously break apart and release energy. So there's that curve. The cool thing about state functions actually is the change in energy between any of these states is just final minus initial. And with state functions, it's great because you can set 0 wherever you want. So in this case, you pick what would be the 0, what should be the reference point.
The bonds just touching.
Right, we could call that 0, and then those would be both higher energy. It turns out,
Isn't it a horizontal asymptote at about 0?
well, where is 0?
So where the graph becomes asymptotical.
This asymptote, or
Nope. Horizontal. Yeah.
I think
And
that's
so the energy comes to about 0, but not quite ever gets to 0, and so the 0 should be slightly above our horizontal asymptote. Yeah, like there. Yeah.
So I can make that 0.
Yeah.
And that's handy. Maybe because that's asymptotic, it's handy for another reason. And if you put them close together, made this the 0, it's a little harder to compare different things. So say if these were different ions, the ions, all systems look about the same when they're spread far apart, whether it's sodium chloride or lithium fluoride. When they're far apart, the energy, that's where you want to compare that. Call that 0, because that's far apart and they're not interacting. Then you can compare when it's a different atom or set of coming together. You can compare where they would be at the minimum, where their preferred distance is, and how low it is, how much energy it takes to break that bond. You can compare them if you make this the 0.
So is this like how we measure bond energies?
That is how you would do it, yeah.
So like, since energies are asymptote and that's our 0, wouldn't we, if like the 0 was there, wouldn't we be saying the energy is negative below it?
Yes.
Like
So
it's gainy.
what
Never mind.
this is whenever you look at these plots, don't think about positive or negative, just think relative to something. This guy here is lower than that. So going here to here, energy goes down. Okay, there's no such thing as positive or negative energy. You can't.
There's just a change.
Yeah, there's just changes. So you can't have negative energy. You can have energy if you gain some more, that's a positive gain, a positive change. If you lose some, that's a negative change. But you don't have negative energy. So, and this is one of the reasons why we could have put 0 down here. And then that would be a positive energy, and that would be a positive energy. Well, that doesn't matter. The difference between them is what matters. Okay? Cool. So that's a good example. Let's do an example with, oh wait, do we want to let's just get rid of part of it, right? We'll do a gas in a piston, and we'll go from here to here. So there's a gas in there. And it expanded, the volume got bigger. And there was this piston here, so in order to get bigger, the gas had to push that wall.
Did the gas have to do work?
The gas had to do work. Are we down with that?
Yeah.
So it's this situation, this situation, the system is doing work.
So in this case, is the system the gas and the piston, or just the
You
gas?
can make whatever you want.
In
Best idea is just make it just the gas.
just the gas.
So the gas is the system. It's doing the work to push back the piston. So, so if then delta E is Q plus W, the system did some work. So we call that, if the system does the work, that tends to lower our energy. That's negative work. So this thing here is going to be a negative number. That's going to make this, get smaller. Tend to make that get smaller. So what does that mean about the temperature of the gas if that happens?
It's going to decrease.
It's going to decrease. Why is that?
If there's negative work done on it.
From Cafe. Go ahead.
So if there's negative energy, internal energy generally corresponds to heat, and so we're going to decrease in heat.
Be careful. Internal energy does not correspond to heat. Energy corresponds to
temperature. You're right, because Q is heat. Q is heat. Okay.
Energy of an ideal gas is the temperature.
Right.
Okay? Those are just direct. You can't change one without the other.
Oh, okay. Yeah. So
the energy change. If you put a delta here, you got to put a delta there.
Yeah. So
the energy can't change in a gas without the temperature changing. It's a good thing about gases. They can't hide the fact that their energy changed. The temperature has to change. Okay?
So if we have a negative delta E, we also have a negative delta T.
For a gas. Same way in reverse. If the energy went up, then the temperature had to go up too. Okay? So, could I do something to get the temperature in this process to get the temperature not to drop? What would I do?
You would change.
add heat.
Yeah, the ways I change the energy are work and heat. Work and heat are the ways I can change the energy. If I want to change the temperature of the gas, that means I want to change its energy. So I could let heat go in at the same time the work is being done, and I could keep the gas at the same temperature.
Could you also pump in like more molecules of the gas?
Yeah.
Would that-
Yeah, let's not change the system though. That starts
that
to
would
get
change
messy.
the gas,
That gets
and that would
messy.
be bad.
That then we'd have to put an N here, or when we would have to keep track of other things. All we want to change is T and not N. Okay. So here's how you can imagine it. The gas is in the piston. It can expand and push against the atmosphere a little bit, do work, but then absorb some heat from the surroundings. Do a little work, absorb a little heat. Do a little work, absorb a little heat. So we can stay at the same temperature as long as it's absorbing the same amount of heat as it's doing work.
Does this have to do with the thing where like you could have a delta E at the beginning and the end of the reaction that won't change, even though like stuff has changed throughout the reaction?
That is, yes, the state function delta E, in this case, if these two things are equal and opposite, that doesn't change. So delta E is 0 as long as you keep the temperature constant, and you do that by doing work and then adding heat. Or the other way, you compress the gas, and if you compress it, you do work on it. So what happens to its temperature? Yeah, so you have to, and how do you cool it down? Let some
A gas cell?
Heat.
Heat.
Do work on it, its temperature goes up, let some of those joules out as heat. Put in a joule of work, that makes the energy go up by a joule. How do you make the energy go down by a joule? Well, either let it do the work again, or let a joule of heat out.
Is this part of the energy is conserved thing?
That's exactly what this is. So, well, energy is conserved, but the energy of the system, the energy change in the system has to equal the energy change in the surroundings in the end. This says the energy in the universe is conserved. This is the first law of thermodynamics. This is one way to say the first law of thermodynamics. This is the other way. So if you take all the energy of, oops, going a little crazy here.
Would it be a negative, like an opposite change, or would it still be like there?
Yeah. I was just gonna do that. So
I was gonna ask that too.
yeah, I'm sorry.
I thought of it. Yay!
They're the
So
same
team.
but they're opposite side. Yes.
Okay, cool.
No, good.
So like one of them would be negative.
Yes.
Okay.
This is what we have to say. So any energy change in the system and any energy changes in the surroundings
Equals 0.
have to be 0. The amount of energy in the universe can't change. The amount of energy we had at the beginning of the universe is the same amount of energy we have now. Okay? All we've done is move it from place to place with heat and work. Okay? That's pretty profound. Pretty profound statement.
Cool.
But this actually helps you understand gases a little better. Remember last time we plotted P and V, and we got a curve. So if we know that PV equals nRT, so say I start right here, and I want the pressure to drop a little at constant volume. So this is going to go down. This is going to stay the same. So what has to happen? Temperature has to decrease. Okay? So going here, the temperature decreases. And remember you were confused about that. We moved around in PV space and the temperature was changing. And this is why the temperature is changing. Okay? So I could then go and increase the volume and keep the pressure constant. So if I want the volume to increase at constant pressure, what do I have to do? So the volume increase the volume, the pressure.
Increase temperature.
Yeah, if you increase the volume, the pressure tends to go down, right? So in order to make it go back up, put the heat in, increase the temperature. So that's the heat going in. That's the same process. The gas expanded, it did a little work. In order to keep it the same temperature, you have to put in some heat. So that's what happens on this path here. But you could bring it back to the same temperature. And those lines will all, those isothermal points all lie along that line that you can plot as P equals T over V. That's just the ideal gas law written as a hyperbola.
And those are all the ones with the same temperature,
Yep,
right?
all these have the same temperature, and if you go off that line, the temperature changes. Okay? Psyched. So let's, okay, I'm babbling on. So are there any questions about, I was going to relate it to entropy next. Do you want to talk about something else before I do that? Yeah, you want to just keep going and talk entropy? Let's look at a different example. So here,